Mars may look like a lifeless desert today, but billions of years ago it was warm, had lakes of liquid water, and was possibly habitable for a short period in its history. But what happened to this ancient paradise? What caused this dramatic transformation? To answer these questions, astronomers have peered into the heart of Mars, and they have found something unexpected. The pulse of life still beats on the red planet. Despite NASA's InSight Mars lander being retired in December, researchers continue to analyze the data collected by the mission. Over the span of 4 years, the InSight lander diligently recorded and examined the auditory landscape of Mars, focusing on the vibrations triggered by seismic activity and meteorite collisions. These acoustical records have yielded significant understandings about the makeup of the planet's internal structure. To truly comprehend the discoveries derived from the seismic data of NASA's InSight mission, it's important to know how the mystery of Earth's core was cracked more than a century ago. It's all a play of waves. To gain insights into the internal structure of Earth, scientists commonly investigate seismic waves, powerful waves that propagate through the planet's interior. Originating from diverse sources such as natural phenomena like earthquakes or human-induced activities like controlled explosions, these waves serve as invaluable tools for scientists as they meticulously examine how seismic waves interact with a wide range of materials. Through careful analysis of their behavior while traversing different substances, seismologists can derive essential properties of these materials. Just as light waves dynamically engage with objects through processes like transmission, reflection, absorption, refraction, polarization, diffraction, or scattering, depending on the composition and wavelength of light, seismic waves also change their behavior depending on the materials encountered. Seismic waves can be classified into 2 primary types, P waves and S waves. P waves, also called primary waves, are compressional waves that generate vibrations in rocks parallel to the direction of wave propagation. Due to their high velocity, they are the first seismic waves to reach a location from the epicenter of an earthquake. S waves, known as secondary waves, are shear waves that cause rocks to vibrate perpendicular to the direction of wave propagation. These waves travel at approximately 60% of the speed of P waves and follow the arrival of P waves. In 1906, British geologist Richard Oldham made a groundbreaking discovery when he observed that seismic waves exhibited notably slower movement within the Earth's core compared to other sections. What further piqued his interest was the realization that S waves could not penetrate the core, while P waves, although capable of traversing it, experienced deflection at the core's boundary. These observations led him to conclude that the outer core is in a liquid state, while the mantle above it remains solid. Our comprehension of Earth's core has been further enhanced through subsequent investigations. In 1936, Inge Lehmann, a Danish seismologist, made an intriguing discovery when she noticed seismic waves bouncing off the inner core, suggesting a transformation from a liquid to a solid state. These pivotal findings, derived from painstaking seismic studies, have played a significant role in demystifying the intricate layers that constitute our planet's core. Now let's jump ahead almost 100 years to explore the Martian interior, where scientists have used the same seismic methods with amazing outcomes. Geology professor Vedran Lekic, a co-author of the study, said, "More than 100 years later, we're applying our knowledge of seismic waves to Mars. With InSight, we're finally discovering what's at the center of Mars and what makes Mars so similar yet distinct from Earth." In 2018, the Mars lander called InSight, which stands for Interior Exploration using Seismic Investigations, Geodesy, and Heat Transport, embarked on a mission to thoroughly examine Mars's crust, mantle, and core. A pivotal objective of this mission involved placing a seismometer, known as the Seismic Experiment for Interior Structure, onto the surface of Mars. The purpose of this instrument was to gauge seismic activity and construct accurate 3-dimensional representations of the planet's internal composition. Throughout its 4-year active mission, InSight captured data on numerous Marsquakes. However, it was in 2021 that the real excitement began. During that year, InSight recorded 2 remarkable incidents on the far side of the planet. One of these was an enormous Marsquake, surpassing any previous detections in size and power. The other event involved a meteorite impact that reverberated across the entire planet. InSight's position on the opposite side of Mars offered a remarkable chance to delve into new frontiers. Not only could the lander study waves that traveled around Mars, but it could also investigate seismic waves penetrating through its very core. This breakthrough granted researchers an unparalleled insight into the seismic waves traversing the depths of Mars. The fascination grew as scientists meticulously compared the travel times of these seismic waves as they journeyed through the core, contrasting them with the waves confined within the Martian mantle. By skillfully integrating this valuable dataset with other seismic and geophysical measurements, they successfully derived estimates for the density and compressibility of the materials encountered by these waves. The findings yielded surprising results. Mars's core exhibited a consistently squishy liquid state, which starkly contrasts with Earth's core. Earth's core is believed to consist of a liquid outer core and a solid inner core, potentially encompassing an even denser innermost core. Additionally, the investigation revealed that Mars's core contained a notable abundance of lighter elements dispersed throughout. On average, these elements contribute approximately 1/5 of the planet's total weight, with sulfur being the most prevalent, followed by smaller quantities of oxygen, carbon, and hydrogen. This unexpected composition serves to underscore the distinctive nature of Mars's geological composition. These discoveries suggest that Mars's core possesses lower density and greater compressibility when compared to Earth's core. The magnetic field on Earth is maintained through a process called geodynamo activity, which occurs within the planet's core. To put it simply, heat travels from the inner core to the outer core, causing currents in the conductive fluid found in the mantle. As the Earth rotates, these currents can twist and form patterns, giving rise to a magnetic field. This magnetic field then interacts with the fluid's motion, resulting in the creation of a secondary magnetic field. This phenomenon, known as the dynamo effect, is responsible for the continuous existence of Earth's magnetic field. Recent investigations into Martian magnetism have indicated that the presence of lighter elements within the planet's core may have had a notable impact on the decline of its dynamo and subsequent loss of its magnetic field. With a deeper comprehension of the composition of Mars' core now at our disposal, we possess enhanced capabilities to reconstruct the historical trajectory of the planet with greater precision. All thanks to InSight lander. Initially, the InSight mission was only supposed to last for about 2 years, but NASA extended the mission for another 2 years. The InSight mission continued to collect data about Mars until the very end, falling silent in December 2022 after dust blocked its solar panels from receiving necessary sunlight. But the treasure trove of data the lander collected during 4 years on the Martian surface has changed the way scientists understand the red planet. We hope you enjoyed this episode and learned something new. Please give us a like and share this video with your friends. If you're hungry for more amazing content like this, why not hit that subscribe button and join our community? We'd love to have you with us for future videos. Thanks for watching, and stay curious.